Hello, welcome back. So today we're going to be looking at some basic wave behavior and then kind of combining some different things, showing you a really cool thing called standing waves. It's a lot cooler if you're in person and you can see me actually set up these standing waves on a elastic cord, but I've got an animation for you guys. You can Google standing waves and probably get some cool videos about that too, but anyway, so when a wave or a wave pulse meets a rigid boundary, which means a boundary that cannot oscillate up and down, that reflected wave pulse is flipped or inverted. Okay, so rigid means flipped. Okay, as opposed to a freely swinging end. So here we've got a loop, and the rope can go up and down with the wave. When a wave reflects off a freely swinging end, it is not inverted. So those are two things that I would know about that. So this is just an animation kind of showing you what's going on with these. So here we've got a fixed end and the wave is flipped. Okay. Here we've got a freely swinging end and the wave pulse is not flipped. So now when a wave meets a different medium, okay, with a different velocity, some of that wave pulse is transmitted into the new medium, and some of it's reflected back in the old medium. So when we start with a heavier medium, so here we've got a thick cord, and we send our incident pulse. That's the pulse that we send down before it reflects and transmits. So we send an incident pulse down. When it reaches that medium, some of that pulse is reflected back. Okay, now it's important to note that it's not inverted if we're going from heavier to lighter. Okay, that's kind of like the freely swinging end, and the transmitted pulse is not flipped either. So and all kinds of things do this when they meet a new medium. They may not do this exact invertedness or not. But when light meets a window, some of it's reflected and some of it's transmitted, and things like that. So this is some wave behavior that we'll see. If we go the flip side of that, and we start with a lighter medium. So here we've got a skinnier rope meeting a heavier rope. When we send our incident pulse down, okay, the reflected pulse is inverted because it's like meeting a rigid object and going to a heavier pulse. And the transmitted pulse is just transmitted like it was before. Okay, so here is what we're. Okay, no animation. Okay, now we just saw that if you sent a pulse and it met a rigid object like a wall, when it reflected back, the pulse is going to be inverted. So here, what are these two pulses? So I've got a blue and a red pulse, and they're going to hit that wall and get inverted, and then they're going to be traveling back this way. What is that going to look like? Well, the blue pulse, which is going to be leading, okay, is going to be flipped, and it wasn't up, now it's a down, okay, and the trailing pulse is flipped. It was a down, now it's an up. But what I want you to realize is that just looking at this picture, it doesn't look like it's flipped. But looking at the colors, you can see that it is flipped because it's traveling the opposite direction. So when I send a pulse down like this, okay, when it reflects back, it looks like it hasn't flipped, but it has. Okay. Now some interesting things happen when we start looking at constructive and destructive interference as well. So let's say you send a full wave pulse down. While the wave is in the process of reflection, you're going to see some interference. So here's my wave pulse that's going to reflect. Okay, so here's my wave pulse that has already reflected, which is going to be a down. Okay, here's the part of the wave pulse that hasn't met the wall yet. So this part right here hasn't met the wall yet, and it's a down. Okay, so meanwhile, the part that hasn't met the wall and the part that has already met the wall and flipped are both down. Okay, so I'm going to get constructive interference. So for a brief moment, the wave is going to get real tall on a down hump. Okay, so I'm going to see a big down hump. And this it introduces what we're going to talk about with standing waves. If waves didn't reflect off of a boundary, and you continue to send waves down a rope or whatever, this is what you would see. But this is not what you see if somebody's holding on to that other end of the rope, or you've got attached to something. You see something completely different. Okay, what you see is a combination of the waves that you're sending down, or the incident waves, okay, interfering with the reflected waves coming back the opposite way. Okay, and that'll make sense when I show you this animation in a little bit. Okay, so here I'm shaking the rope at just the right frequency, so half a wave fits between me and the wall. Okay, now what is this wave going to look like when it's reflected back? Well, it's going to bridge the wall, it's going to reflect, and it's going to be down. Okay, so that way it's going to be reflected down. So meanwhile, okay, so I'm going to continue sending the other half of the wave, which is a down. Okay, so here's the full wave that I've sent. This part of the wave is going to have reflected, and is going to be a down wave over here, which is going to constructively interfere with the wave that I'm still sending. Okay, and I'm going to see constructive interference of the two, and I'm going to get a big down hump. Okay, now if I double my frequency, okay, what's that going to do to my wavelength? Well, it's going to cut it in half. Okay, and now instead of only fitting half the wave, I'm going to be able to fit the full wave between me and the wall. Okay, so now when I send this wave, okay, when it reflects back, what's it going to look like? It's going to look just like this, except traveling the opposite way. Okay, meanwhile, I'm continuing to send waves down. Okay, and the next wave I'm going to send down looks like this. Okay, so when they're on the same string, here's my incident wave that I'm sending, and here's the reflected wave that's coming back. Okay, I'm going to get constructive interference again. Okay, standing waves, and I'm going to show you what a standing wave looks like here, is the result of incident and reflected waves. So what it's going to do is I'm going to get it going here, and this red shows the incident waves. Okay, so and this moves slow, which makes it a little easier to follow. So the red is the incident waves. The dots actually show what the string is doing. Okay, and right now, because there's only one wave on it, the string is doing what the red wave tells it to. And now in a second, the waves are going to start reflecting back, and that's going to be blue waves. Okay, and you're going to see the interference pattern, or the interference of these waves, travel backwards. Okay, with the blue wave. So here it's right here. So here it looks like the waves are moving. Okay. Over here it doesn't look like the waves are moving. It looks like the string is just jiggling back and forth. Okay, but okay, what you can tell is that the wave that you're seeing just oscillate up and down. Okay, it doesn't look like it's moving anywhere. Is the result of incident waves traveling to the right and reflected waves traveling to the left. Okay, and this is a standing wave. Okay, a standing wave has nodes. Okay, the nodes, just like before, where the wave crosses the baseline, but in a standing wave, those nodes are stationary. Okay, they don't move. So if I set up a standing wave on an elastic cord, okay, the parts of the wave will be jiggling like mad, and other parts will be perfectly stationary. Okay, the nodes are perfectly stationary. Okay, and that's pretty much what causes a standing wave. Okay, let's see. Okay, so the red shows the nodes. So these are the nodes, the part of the standing waves where it's stationary. Okay, the yellow are the antinodes, which is either a crest or a trough, whichever it happens to be at that moment. Okay, now was this constructive or destructive interference? I should have had this. Was that constructive or destructive interference? Okay, it was both. Wonder what. Okay. So as those waves came back, well, here, let me just move on. Come back to that. Okay. Now, only certain frequencies will create a standing wave. It's kind of like resonance, where you have to jiggle something at just the right frequency to get resonance, or at one of the just the right frequencies. If you don't, you can be jiggling the spring like mad, and it won't be really vibrating very much. It'll be mostly stationary, which is what you want in something like an airplane wing. On a musical instrument, you want that resonance. You want that standing wave to be set up. Let's see if it's set up. Okay, so here again, just kind of show you constructive interference and destructive interference. So here we have constructive interference and then destructive interference. So constructive interference when it lines up, the crest with the crest, and destructive interference where it lines up with the crest with the trough. Okay, so standing waves are a result of both types of interference. Okay. So if you jiggle at a frequency, and there's several frequencies that'll create a standing wave. I guess technically there's almost an infinite number. But if you jiggle at one of the frequencies in between those, what you're going to get is all destructive interference, where the wave that you send is going to be out of phase with the wave that's being reflected back, and you'll see the rope deaden out. And again, I'll do this for those of you that show up. I'll set up a standing wave, and we'll see the right frequencies for that. Okay. Now, different standing waves. There's for a given distance and string, I can set up a bunch of different standing waves: first, second, third, fourth, fifth, etc. And it just has to do with the number of humps that there is, or antinodes. So here, this is the first, and this is the lowest frequency standing wave that you can set up, where you have half a wave that fits between these. And we're always going to start and end with a node. Okay, we're going to start and end with a node. And the standing wave number is just basically how many antinodes, or how many humps you have. Okay, so the second standing wave, I have a full wavelength fit. In the third standing wave, I've got 1.5 waves that fit between the lengths of the rope, and in the fourth standing wave, I've got two full waves that fit. Okay, so if you pluck a guitar string, it will primarily vibrate at this fundamental, this first harmonic, and that's what creates most of the sound in something like that. So if there's one antinode, it's the first harmonic. There's two antinodes, it's the second harmonic, etc., etc. Okay, waves that can fit, I already kind of went over this. So half a wave between the first two in the first standing wave, one full wave in the second, 1.5 on the third, and 2 full wavelengths on the fourth harmonic, fourth standing wave. So now if we actually calculate the wavelength, okay, the first one, because I could only fit half a wavelength through here, the length of the wave is 2L. So this is my longest wavelength that will create a standing wave. This is my lowest frequency, longest wavelength. For my second standing wave, my harmonic, or my wavelength is just 2, or it's just L. Okay. For my third harmonic, it's 2/3, so 1.5. I get 1.5 waves in there, so it's 2/3 L. And then what you can see is there's a pattern: 2/1, 2/2, 2/3, 2/4. Okay, times L. So you can the length, solving this for length, that's the length of the rope, is equal to n, the harmonic number, times lambda over 2. Okay, so L is the distance between the ends of the ropes, n is your harmonic number, 1 through whatever. Okay, and lambda is your wavelength. So I don't really recommend trying to memorize these, although technically you don't have to, because all the quizzes are open notes and the tests and that sort of thing. But I'd like you to be able to kind of think. The AP exam won't be open notes. Oh, it might be. I don't think so, though. I think it's going to be in person. Okay. So this is the first harmonic. Okay, one antinode. This is the second harmonic. Two antinodes. This is the third harmonic. This is the fourth harmonic, and the fifth harmonic. So each time you just get an extra hump. Okay, so a rope is 1 meter long. What are the wavelengths of the first 4 harmonics? Okay, if a wave travels down the rope at 6 meters per second, what frequency will create the first 4 harmonics? So if the rope is 1 meter, I can fit half a wave on it. So this is equal to 2. Okay, lambda 1 is 2 meters, just twice that. Okay, if this is lambda 2 for my second harmonic, it's just equal to 1 meter because I can fit half a wave. Okay, here I've got 2 or 3 halves of a wave, so it's going to be 2/3 of one. Okay, so that'll give me my third. And then lastly, I've got 2 full waves that fit between that 1 meter, so each one is going to be half a meter. So those are the wavelengths for the first 4 harmonics. So to figure out the frequency, you take the velocity v equals lambda f. Okay, so 6 equals my wavelength, which for the first one is 2 times f, so my frequency is 3 hertz. Okay. If I plug in my wavelength of the second standing wave, I get 6 hertz. I plug in my wavelength for the third standing wave, I get 9 hertz, and then etc. For the fourth one, I get 12 hertz. What I want you to notice is that each of these subsequent frequencies is just a multiple of the first or fundamental frequency. So if you know your fundamental frequency, the second is just twice that. Okay, the third harmonic is going to be just 3 times that, or it's going to be twice that for the, it's going to be 3 times that, yeah. Okay, and for the fourth harmonic, it's just going to be 4 times that. So that's a quick and dirty trick to keeping your memory bank about standing waves. This is where I would normally do that. Okay. So that is it for the day. Good luck, work on your problems, and we'll talk to you soon.